Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on February 11th, 2026, about 12 days ago. It introduces a framework called VESPO that maintains stable training even when data staleness ratios hit 64 times, significantly outperforming current baselines in asynchronous reinforcement learning. The paper is titled VESPO, Variational Sequence Level Soft Policy Optimization for Stable Off-Policy LLM Training. And, as we'll see later, the results on mathematical reasoning benchmarks are really impressive. And for those interested in the implementation, the authors have shared their code on GitHub. Figure 1 illustrates the core concept and its impact on stability. The diagram on the left shows how the method finds an optimal proposal distribution, labeled Q star. It positions this proposal between the stale behavior policy and the current target policy, balancing them to minimize divergence while strictly constraining variance. The plot on the right confirms the benefit by tracking training reward over 1,500 gradient steps. While the green line for SAPO suffers catastrophic crashes and the orange GSPO curve eventually collapses, the red line for VESPO remains consistently high and stable. Well, Figure 2 digs into the mechanism by comparing the surrogate objectives and gradient scaling factors. The top row plots the objective function, where the blue line for hard clipping hits a ceiling abruptly. In contrast, the red curve for VESPO is smooth and differentiable everywhere. The bottom row shows the actual gradient scaling. Here, the difference is stark. While hard clipping drops instantly at the threshold, VESPO's red line peaks near 1 and decays smoothly, effectively suppressing outliers without jarring discontinuities. So, having established the mechanism, Table 1 presents the main performance results with a staleness ratio of 8. It compares 3 model scales across rigorous benchmarks like AM and Math 500. You can see that VESPO, shown in the bottom row of each section, consistently secures the highest average scores. The performance gap is most notable in the bottom section for the QN330B mixture of experts model. Here, the method reaches 57.2% accuracy, beating the strongest baseline by over 2 points, which suggests it successfully mitigates the instability specific to these complex architectures. Alright, while Table 1 fixed the staleness ratio at 8, Table 2 now pushes the limits by varying that ratio, n, from 4 all the way up to 64. This measures how well the method handles stale data during asynchronous training. Looking at the bottom block where n is 64, the baselines struggle significantly. SAPO collapses to just 18.4% accuracy, while GRPO and GSPO drop to the mid-40s. In contrast, VESPO holds its ground with a robust 58.5% average, confirming it scales effectively even with significant training lags. Well, Figure 4 unpacks the training dynamics behind those summary statistics. Each row here represents a different staleness level, while the columns track key metrics like training reward and response length. If you follow the red line for VESPO in the first column, you see it remains smooth and stable across every single row. In contrast, the green line for SAPO in the top response length graph suffers from a massive length explosion, spiking to 15,000 tokens before the model collapses. Finally, the blue line for GRPO in the entropy column drops much faster, indicating it stops exploring too early. So, while the previous figure simulated fixed delays, Figure 5 tests fully asynchronous training where data lags vary unpredictably. Here, the red line for VESPO demonstrates remarkable stability compared to the baselines. Notice the bottom right plots for PG loss and gradient norm. The blue line for GRPO shows massive chaotic spikes that signal severe instability. Similarly, the green line for SAPO in the top accuracy plots crashes almost immediately. In contrast, VESPO maintains a smooth trajectory, securing the highest final reward without these catastrophic failures. Wrapping up, 2 takeaways stand out. VESPO solves the critical instability of off-policy training by replacing heuristic clipping with a principled variational kernel. This approach eliminates length bias and enables robust scaling for complex architectures like mixture of experts, even in fully asynchronous setups. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.